Hello all, this is the assignment discussion session for week 2 for fiber optic communication technology course. The course topic is mainly on LED, its working principle, efficiency, and its modulation based characteristics, and why we need a laser diode and other resonator concepts. So let us go to the question. The forward current through a gallium arsenide phosphide red LED, which having a refractive index of 3.5 at 850 nanometer, is 35 milliampere at 3 volt, operates at room temperature. The internal quantum efficiency is 0.55 and with a carrier lifetime of 1.25 nanoseconds. So this is the given data. The first part of question is about what is the carrier injection rate. You have to write it in these units. So we'll try to solve this. So let us first start with writing down what are the given parameters. So the refractive index is given at 3.5. The wavelength is given as 850 nanometer. The forward current is given as 35 milliampere. The voltage is given as 3 volt. And the internal quantum efficiency is given as 0.55. And the carrier lifetime at 1.25 nanoseconds. Coming to the question, the carrier injection rate is given by Rij is equal to I by E, where I is the current and E is the charge of an electron. So this is a universal constant, E, which is 1.6 into 10 power minus 19 coulomb. So it's direct substitution with 35 milliampere by E, which is 2.187 into 10 power 17 per second, which is a rate, carrier injection rate. Moving on to the second part. At this rate, from the previous question, the optical power generated by the LED would be dash milliwatt. So it is asked to find out what is the optical power generated. So we have the value, the injection rate, which we found already. Now, the equation for optical power generated is eta internal efficiency into h nu into I by E. The I by E value, which we have already found out, is this value, and then h is the Planck's constant, which is a universal constant again, and eta internal efficiency, which is internal quantum efficiency, which is given as 0.55, and now we have nu, which is the frequency. Since this is given in wavelength, which is 850 nanometer, we are doing c by lambda, where c is the speed of light. So expanding this and substituting the values, we get the optical power generated as 28 milliwatt. This is the optical power generated by the LED. So we call it P internal. Now we will move to the third part. Of the optical power which is generated internally, how much will be the power available at the output? Now the equation for power output is given by eta external, which means external quantum efficiency into P internal. Now the equation for external quantum efficiency is 1 by n into n plus 1 square. So we have n equal to 3.5 here. So substituting those values, we get the output optical power to be 396.19 microwatt. Now going to the next part of the question, we get from the above data, what is the slope efficiency of the LED? So we already see the output power is 396.19 microwatt. So the slope efficiency is given by P out by I. So I is the current which generates this power, and P out is what we got in previous part of the question. So division, we get 11.32 milliwatt per ampere. So moving on to the fourth part. So this is the fifth part of the question. So it is asked to find out what is the wall plug efficiency of the LED. So what is wall plug efficiency? It is the ratio of the optical power which we can extract out of the LED versus the input electrical power we have supplied to the LED. Now the input electrical power can be given by V into I, which is 3 volt into 35 milliampere, and the output optical power we have found it in previous step. P out is equal to 396.19 microwatt. Substituting these values, we get the wall plug efficiency to be 0.37%. What this means is only we are able to convert 0.37 percentage of the power uh, we have supplied to the LED as output optical power. Now moving on to the last part of the question, it is asked to find out the spectral width emitted by the LED in units of terahertz. So the spectral width, it is represented as full width half maximum, FWHM, is given by 1.8 kT by H, where K is the Boltzmann constant and H is the Planck's constant and T is the temperature. So in the question, it is given as operating in room temperature, which is a standard 300 Kelvin. So substituting the values, uh, we get it's 11.25 terahertz. Hope all of you have understood how to solve this question. Thank you.